वेलकम। सो इन दिस वीडियो वी विल लर्न अबाउट दी बफर सॉल्यूशंस। तो हम जानेंगे कि बफर सॉल्यूशंस क्या होते हैं, और आपका जो इम्पोर्टेंट जो बफर का एग्जांपल है वो ब्लड है। ब्लड बफर कैसे करता है वो जानेंगे। मिल्क एक बफर का एग्जांपल है, तो मिल्क कैसे बफर एक्ट करता है हम वो जानेंगे। ठीक है, तो लेट अस फर्स्ट अबाउट द बफर। सो हाउ विल डिफाइन बफर? बफर सॉल्यूशंस आर those solution which resist a change in its pH on addition of small quantity of acid or base. So if you are adding small quantity, remember there it is small quantity, not that you are adding extra large amount of strong acid or strong base, then it won't able to maintain the pH. So a solution which resists change in pH on addition of small quantity of acid or base is called buffer solution, and thus buffer serving reserved acidity and reserved alkalinity. So they reserve acidity also, the alkalinity also. So if you are adding acid, then that will be pH will be maintained. If you are adding base, then also the pH will be maintained. That we will see in the coming slides. Now if you have a distilled water solution, distilled water pH is 7. You know that distilled water pH is 7, and if you add HCl, a drop of HCl to it, then you will see that pH will reach to around 2. And if you add a drop of NH solution to it, then pH increase to 13. ठीक है, बट इफ यू हैव अमोनियम एसिटेट सॉल्यूशन, so अमोनियम एसिटेट is acting as buffer, and if you add 1 ml of same HCl or NaOH in it, then the pH won't change. pH will be remaining the same. So it is a buffer solution. So the pH won't change if you are adding 1 ml of both the acid or the base, then the pH of the solution won't change. Similarly, if the example of NaCl solution is there, NaCl is also in neutral, around neutral. So then this change will happen because there is no buffer. But if a buffer is there, even if you are adding 1 ml of acid or base to the ammonium acetate solution, then pH won't change. Okay, so this property is known as the buffer action, and we will see in a while that what is the mechanism of action, how amino acetate is acting as a buffer, or how any other acid acting as buffer. Now a buffer solution usually consists of mixture of weak acid and its salt with a strong base. So this is if a weak acid is there, acidic buffer with this type of buffer is called as the acidic buffer. ठीक है, so buffer solution consists of mixture of weak acid and its salt. जैसे आपका एसिटिक एसिड एक एसिड हो गया, इसका salt of the same acid with strong base. So NaOH is a strong base here, so this salt is formed from NaOH. So it's salt with a strong base, that is the acidic buffer. The example of basic buffer is ammonium hydroxide, that is weak base, and it's salt with a strong acid. Strong acid here is HCl, so this Cl is coming from HCl. Okay, so this if we see that NaOH is there, then we know that this is a strong base, so its conjugate acid will be weak, so this is inactive. So similarly here Cl minus will be weak, so these are not affecting the reaction, that we will see in a while. So they are not participating when you are adding acid or base, then they will be inactive in the solution, that will see in a while. Then solution of any salt of weak acid or weak base, ammonium acetate can also show the buffering capacity. I have told you that ammonium, this is a solution of any salt of a weak acid and weak base. So here you see that ammonium hydroxide is a weak base, and then your acetate, that is weak base example is acetate is there, say sodium acetate, or the acetic acid is there. Then if acetic acid is from acetic acid, acetate is coming, from ammonium hydroxide ammonium is coming. So these are the this is the salt of weak acid and weak base, and this also show the buffer capacity. Okay, then we see in the file what the meaning. Now coming to acidic buffer. Acidic buffer, I told you, a buffer solution containing large amount of weak acid and its salt with a strong base is termed as acidic buffer. This I have told you. Now such buffer solution have pH on the acidic side. They are having pH on the acidic side, so obviously, and pH is less than 7 at 298 Kelvin. Okay. Now pH of acid buffer is given by equation. This is known as Henderson-Hasselbalch equation. Henderson-Hasselbalch equation. ठीक है, pH equal to pKa plus log of salt by acid. Now example of acidic buffer, I told you acetic acid and sodium acetate, and then mixture of acetic acid and sodium acetate act as a buffer solution with a pH of about 4.75, and K is the acid dissociation constant of weak acid. Now K is the acid dissociation constant, and more is the value of Ka, more is the strength of the acid. More is the value of pKa, less is the strength of the weak acid. Please understand, pKa is the negative of logarithm of Ka. So more is the Ka, so more will be the acidic strength of the more is the strength of the acid, and more is the pK, lower is the strength of the acid. Okay, then coming to basic buffer, similarly in the same way, buffer solutions containing relatively large amount of weak base and its salt with strong acid is termed as basic buffer. So weak base is there, इसका salt इसके साथ strong acid के साथ, जैसे हमने देखा अमोनियम हाइड्रोक्साइड है, ये weak base है, और इसका salt किसके साथ, HCl के साथ, HCl के साथ यानी strong acid के साथ, तो is termed as base buffer. And such buffer have a pH on the alkaline side, pH is higher than 7 at 98 Kelvin. इनकी जो इन बफर की जो pH होती है वो अल्कलाइन साइड पे होगी obviously. And mixture of ammonium chloride and ammonium hydroxide act as a buffer solution with a pH of about 9.25. तो अगर आप अमोनियम क्लोराइड और अमोनियम हाइड्रोक्साइड का मिक्सचर है, उसकी जो pH रहती है वो जनरली जो है 9.25 के पास रहती है. And again this is also Henderson-Hasselbalch equation for a buffer consisting of weak base and its salt with strong acid. So this is POH equal to PKB, that is for basic buffer, this equation to be used, POH plus PKB plus log of salt divided by acid. Again PKB more is the KPB, is the dissociation constant for weak base, more is the value of the Kb, more is the strength of the basicity of the base, or more KPB means base is strong, and if Kb is less, then strength of the base is weak. Okay, and this is inverse of PKB. PKB is higher, then your base is having lower strength, and if PK is lower, then your base is having higher strength. So PKB is opposite to that of the KB. Now let us see about the buffer capacity and buffer range. Now effectiveness of any buffer is described by buffer capacity. Now the definition of buffer capacity: the number of equivalents of strong acid or strong base required to change the pH of 1 liter of buffer solution by 1 unit, keeping the total amount of acid and salt in the buffer constant. So this is the definition of buffer capacity. The buffer capacity means the ability of the buffer system to resist the change in pH, and it is defined as the number of equivalents of strong acid or strong base required to change the pH of 1 liter of buffer solution by 1 unit, keeping the total amount of acid and salt as constant. Now buffer capacity of a buffer is maximum when pH of acid equal to salt, and the acid to salt or base to salt ratio is 1. It contains equal number of the acid and salt. So here if we say the buffer is constant, say if the salt becomes equal to acid, the concentration of salt is equal to the central concentration of acid. So here this will become 1 and L11 is 0. So your POH here equal to PKB, and here it will be for acid it will be pH equal to pKa. So here pH is equal to and obviously at this point the buffer capacity will be maximum, and at this point what will be there, buffer capacity of the buffer is maximum when the concentration of acid to salt and the base to salt is equal to 1. This ratio becomes 1, that is the equal number of moles of acids and salt are there, or equal moles of base and salt are there, then your buffer capacity of the buffer may be acidic or basic, that will be maximum. So all buffer solution remain effective over a small range. They are effective over a small range only. Note that if you are varying a range to a broader pH, then they won't be effective. So this pH range is characteristic of buffer and stabilized buffer. इसी को हम buffer range कहते हैं. ठीक है, इसके बाद एक टर्म और आती है बफरिंग इंडेक्स. इसको हम डिफाइन कर लेते हैं कि डिफरेंशियल रेशियो ऑफ इंक्रीज इन अमाउंट ऑफ स्ट्रॉन्ग एसिड टू और स्ट्रॉन्ग बेस एडेड टू पीएच वेरिएशन. सो दिस इज डिफरेंशियल रेशियो ऑफ द अमाउंट ऑफ स्ट्रॉन्ग एसिड और स्ट्रॉन्ग बेस टू द pH variation. Differential ratio of increase in the amount of strong acid or strong base added to the pH variation is nothing but the buffering index. So N is the equivalent of added strong base, whereas N is the equivalent of adding strong acid or strong base is the differential ratio of increase in amount of strong acid or strong base to the pH variation. Differential ratio. Note that addition of dn moles of acid will change pH by exactly the same value but in the opposite direction. ठीक है, so similarly it means of acid or base, that means now field of application of both notion is different, although the meaning is same. Buffering capacity and buffering index is just the same way of telling the same thing, that but the buffer capacity is mostly used in quantitative chemical analysis, whereas buffer index is a term which is generally used to study the biological system. This is the difference. Although the notion is same, notion of the buffer capacity and buffering index is same, that is both are conveying the same meaning, that is the ability of any buffer solution to resist or to resist the change in pH on addition of small quantity of acid or base, but the way we are defining is different, and also in buffer capacity is application in quantitative chemical analysis, and buffer index is having application in the biological systems. Now let's see mechanism of buffer action. This is very important, how buffer is showing the buffering effect that we have to see. So when strong acid is added, proton cells chemist by the salt component of the buffer system. This we'll see in the coming slide. And when an alkali is added, acid component will get deprotonated, and alkali combines with the proton to form water. This also see. Now let us see the example of acetate buffer. So if this is a example of acetate buffer, so acetic acid is getting dissociated to acetate ion and the hydrogen ion, and the sodium acetate is getting dissociated to sodium ion and the acetate ion. Now what happens is that if H plus is coming, small quantity of H plus is coming, then what will happen is that it will bind with the acetic acid. So it will, this hydrogen ion will get stuck in the acetic acid and won't get removed. So no, it won't be removed, then dissociated. Why? Because one is that common ion effect, that if acetate ion is common, so because of the common ion effect, it won't dissociate, and also already it is a weak acid, so it is no dissociate. So your pH won't change. Okay, so what is happening? So if you are adding H plus ion in an acetate buffer, then your acetate of the coming from the salt will participate, and the H plus will combine with this acetate, and then we will have the acetic acid. And this acetic acid won't get dissociated because of the first is common ion is there, acetate ion is the common, and then also this weak acid is dissociation is already very poor, so pH won't change. Now if you are adding the alkali, say OH you are adding, then it will combine with the it can combine with N plus also H plus, but it won't combine with this because it is inactive. I've told you that NOH is coming from strong base, so it is weak conjugate acid. So weak conjugate acid, this will remain inactive, this will remain as such in the solution, so it will be OH minus will be combining with the H plus, and then we will have the water molecule. Now since there is loss of hydrogen ion, it is expected that pH has changed, but this loss of hydrogen ion, is compensated by the dissociation of this acetic acid. So this dissociation of acetic acid, this loss is compensated. This is the mechanism. So we have seen that either we are adding acid or we are adding base, the pH of the buffer is not changing, and the mechanism I've told you. So we can take another example. Say we have ammonium hydroxide buffer. Say ammonium hydroxide will give you, and similarly you have ammonium chloride. Okay, now this is ammonium hydroxide buffer. Now if you add say OH minus first in this, so what will happen? This OH minus will combine with ammonium ion to form the ammonium hydroxide. Now again this is the weak acid, this is the weak base, and also the common ion, ammonium ion is there, common ion, so this won't get dissociated, so pH won't change. So this means if you are adding the base and giving the OH minus ions, this will combine with the ammonium ion to form the ammonium hydroxide, and since this is a weak base and also this is a common ion effect, because of the common ion, pH won't change. Now if you are adding H plus ion, now this ammonium hydroxide is coming, this H plus can combine with HCl minus also H minus, but Cl minus is weak conjugate base, and also it's inactive in the solution, it is not reacting with any ion, so it will combine with the OH minus ions, and we can see that there will be formation of H2O, and we have seen that there is loss of hydroxyl ion is there, and this is compensated by the dissociation of ammonium hydroxide. So therefore pH is not changing. So in this way we can explain the mechanism of action of any type of buffer by demonstrating that on addition of any acid or base, there is no change in the pH. Now let us see example of blood which is acting as buffer. Okay, so now blood is a very good example of a buffer, and the main system which is there, which is maintaining the pH of the solution to pH of the blood as 7.4 is the bicarbonate buffer. bicarbonate buffer. So bicarbonate buffer means that carbonic acid and NaHCO3. So this is a bicarbonate buffer. Now how the reactions are happening. So we know that when cell metabolisms are taking place, cell metabolism is happening, and then carbon dioxide is coming out from the cell and diffusing into the plasma where water is there. So this carbon dioxide will react with water to form the carbonic acid. So this carbonic acid is formed, and then in solution carbonic acid will dissociate as H plus HCO3 minus. Okay, now this HCO3 will combine with sodium to form the sodium bicarbonate. This is sodium bicarbonate. Okay, now the ratio of sodium carbonate, that is NaHCO3, is to carbonate, or is to carbonic acid. So if you see that the ratio of NaCO3 and carbonic acid, that's to CO3 in blood plasma, is around 20.1, which is sufficient to maintain the pH of blood as 7.4. Okay, so this way you know your system is forming that how a bicarbonate buffer system is existing in blood, that I have told you. That first you have to write that the major system which is contributing to the buffer, which acting as buffer in the plasma of the blood, is the bicarbonate buffer system, which keeps the pH of the blood at pH 7.4. And then you know that when metabolism of the cells happens, then carbon dioxide diffuses into plasma where react with water to form the carbonic acid. This carbonic acid in solution dissociate as H plus ion and the carbonate ions, and then this bicarbonate can combine with the sodium to form the sodium bicarbonate. And in blood plasma, the ratio of sodium bicarbonate to carbonic acid is around 20:1, which is sufficient to maintain the pH of the blood as 7.4. Okay, now we will see we have seen that in blood we have the buffer system, which is the that is carbonic acid and NaCO3. Okay, and the ratio is 1:20. Okay, this is sufficient to maintain the pH of blood or plasma as the 7.4. This I have told you. Okay, now let's see what happens is that when metabolism is happening, cell metabolism is happening, some of the acids which are released, like lactic acid is there, phosphoric acid is there, now acetoacetic acid is there, acetic acid, and then hydroxybutyric acid is there, beta hydroxy butyric acid. Now these acids will tend to change the pH of the blood, which is harmful. So nature has made it in such a way that your bicarbonate system will come into action, and then it will prevent the change on pH. How? So let's see how. So this is carbonate ion, so you know that it gets associated to plus carbonate, and then you have NaCO3 also, which will get dissociated to NH plus carbonate ion. Okay, now what is there, that is lactic acid is coming from the cells as a result of metabolism, so it will provide H plus ion. Now this H plus ion will react with this carbonate to form a carbonic acid. Again, the way I have told you that this is weak acid, and again common ion is there, so dissociation is prevented. So in this way pH won't change. But in this, what is happening is that if there is an enzyme which is known as carbonic anhydrase, that will act on this carbonic acid, that is carbonic anhydrase will act on this carbonic acid. Then we will have the water and the carbon dioxide. Okay, so this carbonic anhydrase will act on the carbonic acid, we will have water and the carbon dioxide. Right, now this carbon dioxide will get will diffuse into the lungs and is eliminated by expiration. So this will get diffused into the lungs and will be expelled by expiration, that is the breathing out. So expiring, so this will be removed. So this will be removed and the pH of the plasma won't change. Okay, so I'm again repeating, as a result of metabolism in cells, some of the acids are releasing, like lactic acid, phosphoric acid, acetoacetic acid, beta hydroxybutyric acid. So when this coming into the plasma, this is expected that the pH of the plasma will change, but because of the bicarbonate system, that is bicarbonate buffer, which consisting of carbonic acid and sodium bicarbonate, ratio I've told you 21:20, this change won't happen, the pH change won't happen. Why? Because here if H plus is coming, that from the lactic acid or any of the acid which I've told you, then it will combine with the carbonate ion to form the carbonic acid, and this will be acted by carbonic anhydrase. Carbon dioxide will release, will diffuse into the electron, and by expiration it will remove outside the body. So pH plasma won't change. And also you can write that this is a weak acid, and also the common ion effect dissociation is minimum. Now if say anyhow if alkali is adding, so if any alkali substance is getting added into the plasma, is coming into the plasma, then it will react with the H plus ion to form the water molecule. Now since water molecule is forming, and then a loss of hydrogen ion is there, this is compensated by the release of hydrogen ion from the carbonic acid, hence the pH won't change. So hence the pH of the blood is maintained at pH 7.4. Okay, so this is how the blood is acting as buffer. If somebody asks you explain blood mechanism of blood as acting as buffer, so this way you have to explain, starting from that how the carbonic acid and the sodium bicarbonate system originate in plasma, and then how it is preventing any change in pH on addition of or on arrival of any acid or alkali in the plasma. That you have to explain in this way. So now let us see the importance of buffer. Importance of buffer. So we know that many chemical reactions are affected by acidity of the solution in which they occur. In order for a particular reaction to occur or to occur at a appropriate rate, the pH of the reaction mediums must be controlled, and such control is provided by the buffer solution. So some of the chemical reactions which are taking, if you want to maintain the pH in the solution, pH is changing, then the rate of the reaction will be affected. So in this way, that buffer solution are to help, and then which are the solution which are maintain the particular pH. Then buffer help in organism in carrying out the biochemical reaction in a narrow range of pH. So I've told you that pure plasma is there, so their pH is to be maintained, and some of the biochemical reaction which are carrying out are to be carried out at a narrow range of pH. So buffer are again coming into action. So most biological molecules contain active group atoms which may be charged to neutral depending on the pH. So pH if not maintained, then molecules will get converted to either charged or in different form, and again that is also to be prevented. So has a significant amount of biological activity of the milk. In multicellular organism, the fluid within the cell and the fluid surrounding the cells have a characteristic and nearly constant pH. So this pH should not change, otherwise organisms it will be harmful, otherwise we will die. So buffers are helpful in many biological experiments also which are being carried out in lab. So some of the biological experiments which are carried out, they're absolutely that during when we are carrying the in vitro study, so saliva pH, then intestinal pH, gastric pH is to be maintained by using the buffer. So they are helpful in maintaining many carrying out the biological experiment. Now buffers protect the cell and tissue from sudden change in pH also. They also protect the cells and tissue that I will told you. So these are the importance of buffer. So mainly the buffers are being used in laboratory to maintain the pH when during a particular chemical reaction, and also during biochemical reactions which are happening, and also in I've already told that in humans it is very much necessary that all the fluids which is there in the human body must be maintained. pH of the fluids must be maintained in order for an organism to carry out the biochemical reactions which are taking place in the body. Okay, now coming to Henderson-Hasselbalch equation. Okay, now Henderson-Hasselbalch equation, how to derive it? What is Henderson-Hasselbalch equation? So how to derive it? Let's see. Say if you have acetic acid is there, CS3 CO minus COH. Let us now see the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation and how to derive it. So pH equal to pKa plus log of salt by acid. Okay, now so we have acetate buffer CS3COH gives you CS3CO minus plus H plus, and we have acetate also CS3CONa so which get completely dissociated into solution, that is CH3 CO minus plus Na plus. Okay, now this is the state buffer I have told you. Now I have to derive this equation, that Henderson has, how to derive the Henderson-Hasselbalch. So I will write the K for this direction, that is dissociation constant is given by CH3 CO minus H plus divided by CH3 COH. Okay, so this is Ka. So if you want to rearrange it, HA plus equal to Ka into acetic acid CH3 COH divided by CH3 CO minus. Okay, now take logarithm on both side. Here also it will come log, and if you put negative here also it will come negative. Okay, so this way, so it will become minus log Ka, and if you want to write here minus will be there, so plus log of CH3 CO minus divided by CH3 COH. Okay, now this will be minus log K is nothing but the pK plus log of CH3 CO minus को हम लिख सकते हैं CH3 CO Na divided by CH3 COH. ठीक है, so what I want to say here, this is I can write here also that pH is equal to pKa plus log of salt divided by log of acid. So why I have changed this acetate ion to sodium acetate, because we know that sodium acetate is a strong electrolyte, so it will get completely dissociated in the solution. So and here acetic acid dissociating to a very small extent, so I can consider, I can assume that all the acetate ion is coming from the sodium acetate only and not from the acetic acid. So I can write the concentration of the sodium acetate is around equal to the CH3, that is acetate ion, because these acetate ion are majorly coming from the sodium acetate. So I can replace the acetate with the sodium acetate, and in this way I have derived the equation for calculating the pH of the buffer solution when pK is given. So pH of the buffer solution when pK is given, and the concentration of the salt and the acids are given, I can calculate using the Henderson-Hasselbalch equation. This is derived for weak acid, the salt this is derived for the acidic buffer, and if you want to derive for basic buffer, that also we can derive. Let us now derive it for a basic buffer. So we have a basic buffer which is consisting of ammonium hydroxide and ammonium chloride. Okay, so this is a weak acid buffer, ammonium hydroxide buffer. Now if you want to write the Kb value, that is dissociation constant for weak base, that is this ammonium hydroxide, so here it will be NH4 OH minus divided by your NH4 OH concentration. Okay, now so in this equation we'll have OH minus, I can rearrange it into Kb into NH4 OH divided by NH4 plus. Okay, now if you want to write I will take logarithm on both sides. Logarithm of hydroxyl ions equal to logarithm of all this thing, that is Kb into NH4OH divided by NH4 plus. Okay, now negative of logarithm I will take both side negative, and then POH is equal to, here it will be minus log Kb, that is equal to PKb. Here minus log will be there, so minus log of ammonium hydroxide divided by NH4 plus. So this will be equal to PKb. So to replace this, nice, I can write here positive log of NH4 plus divided by NH4 OH. So I can assume that this NH4 plus is coming from, all this NH4 is coming from ammonium chloride. This is a strong electrolyte. It is a strong electrolyte, so it can completely dissociate it from the solution. So I can assume that all the ammonium ions coming from the ammonium chloride. So I can replace ammonium ion as the equation will become pH equal to the pKb plus log of ammonium chloride divided by ammonium hydroxide, which is nothing but this is the salt divided by base. Okay, and reason I can give here that NH4 plus ion concentration is around equivalent to the ammonium chloride concentration, as it can be assumed all ammonium ion coming from the ammonium chloride. So this is your Henderson-Hasselbalch equation for calculating the pH or basic buffer. This way we can derive the Henderson-Hasselbalch equation for both weak acid as well as weak base. Okay, now let us see the importance of Henderson-Hasselbalch equation. What is it used for? So I have told you that it is used to calculate the pH of any weak acid solution or weak basic buffer solution. We can calculate the pH. Apart from it, we can calculate the pH, pH, pK, pKb. If we can give one is given, we can calculate the other. So pK is given, we can calculate the pH. pKb is given, we can calculate the pH also. And knowing the concentration of the salt and acid and base. Now, to know how the buffer solution resist major changes in pH when smaller down, so mechanism of buffer action can also be understood by the Henderson-Hasselbalch equation. Now, also to describe a buffer solution and determine the preparation of acidic or basic buffer solution. So, in chemistry, in experiment what you are doing, you have to most of the time preparing the buffer solution. When you will be given the pK value and the concentration of any one of the salt or the base is given, then you can calculate the pH what will be the pKa, and pH is given, pK is given, then the concentration of salt and the acid or salt and the base which is required to prepare the buffer, that can also be determined using Henderson-Hasselbalch equation. And also we can evaluate the relative strength. If we know the value of Kb and Kb, then we can have the relative strength of the conjugate acid or conjugate base. So if K is more is the strength of the acid. If Kb is more is the strength of the base. To determine whether a given aqueous solution of salt is acidic or basic or neutral, depending on the given values of Kb for the conjugate acid base pair, we can also determine whether a aqueous solution of salt is acidic or basic. This we'll see in the next when we study the start hydrolysis. Also, we can determine the isoelectric point also, pH at which the proteins will carry neither as won't carry any charge. So we can determine the isoelectric point of different proteins also using Henderson-Hasselbalch equation. Now this derivation I have already told you, taking the example of acetic acid. And now there are some limitations of Henderson-Hasselbalch equation. Let's say that Henderson-Hasselbalch equation is valid only when it contains equilibrium concentration of acid and the conjugate base. So their action to be in equilibrium. Then if the acids and the conjugate bases are not in equilibrium concentration, that is the equilibrium is not established, then this equation won't be valid. So I've already told you that this is valid only when we have the equilibrium concentration of the acid and the conjugate base. In case of solution which are containing no weak acid or no weak base, equilibrium concentration can be far from those predicted by the neutralization stoichiometry. So this is to say that Henderson-Hasselbalch equation is valid for only weak acid or weak bases, not for the strong acids or for medium or moderate strength of the acids. For those acids it's not valid. And pK value above 2.5 dissociate too slowly. This means pK above, below 2.5 means that K is more, that is more acidic. Dissociate slowly, and use of the pH prediction can give wrong results, especially in case of dilute solution. So if pK is below 2.5, that is the K is, it is more acidic, then and then it will dissociate to 0, and then equilibrium concentration will be not attained, and then Henderson-Hasselbalch equation for pH prediction can give wrong results. Okay, and for solution above 10 millimolar, one more point is that for solution above 10 millimolar, that more concentrated and acid weaker than pKa less 0. That pK greater than equal to 2.5, this will give result which is with acceptable error, and this holds good for bases also with pKb greater than equal to 2.5. So what I've told you that concentration for solution above 10 millimolar and acid which are weaker. So weaker acid which are pK greater than equal to 2.5, Henderson gives with acceptable error, and same holds good for the basis with pKb greater than equal to 2.5. So very dilute solutions also, these are not Henderson-Hasselbalch equation is not applicable. Now if you want to calculate the pH of polyprotic acid, say you have example, say protic acid is there which is having 3 pKs, likewise citric acid is there which is having pK 3 pK, pK1 1.963, pK2 7.19, and pK3 12.35. Citric acid having pK1 3.128, pK2 4.761, pK3 5. So Henderson-Hasselbalch equation can be used to for the pH calculation of polyprotic acids as long as the conjugative pK values differ by at least 2. So difference would be at least by 2. So here we can take 1.9 and 7.5 difference more than 2. 12 and 7 difference is more than 2. Difference is more than 2. So in this way we can calculate the pK of phosphoric acid buffer but not of the citric acid buffer, where the difference between the conjugative pKs is less than 2. Here it is 3 and 4 less than 2. Again here 4 and 5, this is less than 2. So we can apply Henderson equation for determine the pK values for the pH of phosphoric acid buffers, and but not for the citric acid buffers. Okay, so it becomes necessary to determine the pH of the solution directly rather than depending on the above equation. So for citric acid solution, this is the drawback. So these are the limitation of Henderson-Hasselbalch equation. Main point is that this is Henderson-Hasselbalch equation can be applied for only those solutions which are having concentration greater than 10 millimolar and acids weaker than pK greater than equal to 2.5. Henderson equation gives results with acceptable, and the same holds good for the bases with pKb 2.5.